Hello wonderful person, this is Anton, and today we're going to be talking about a discovery of yet another very unusual planet, and not just the planet, but the star itself seems to be really weird as well. And the reason for this weirdness is in the way it orbits around the galaxy. So first of all, this new discovery comes from the NASA's TESS telescope that has been pretty much actively looking at the night skies for the past few years now. And since we've already confirmed over 4,000 different exoplanets out there, it's no surprise that more and more exoplanets turn out to be a lot different from what we imagine them to be. At the same time, another really exciting mission is from the so-called ESA or European Space Agency, and this is the so-called Gaia Telescope, which is responsible for, well, actually forming one of the most comprehensive 3D maps of the nearby moving objects around the solar system. More specifically, it's already been able to identify close to about 2 billion different stars with extremely precise motion. But when some scientists decided to combine the data from TESS telescope with the data from the Gaia telescope, they realized that there were quite a few stars out there that do have unusual motion around the galaxy. Well, first of all, let's briefly talk about the galaxy. Now, this right here is what a typical, animation or a typical simulation would show us the Milky Way to look like, but as I mentioned in previous videos, this is very simplified and more or less actually is incorrect. More specifically today, we're going to be talking about this part, the edge view of the galaxy. Here, if you look at it, it does seem to be relatively flat and relatively thin. And we know for a fact that our galaxy is actually not flat at all, it is curved, it's basically a relatively warped and also wobbling galaxy, and I've discussed this in one of the previous videos. But at the same time, this doesn't actually show you what's happening in the regions around the galaxy itself. As you see from this image right here, our galaxy and many other so-called spiral galaxies do have several layers within them. Now, for the most part, most of the visual objects, basically all of the stars including our sun, are in this really thin disk, which is actually what you're seeing here. So the only thing that's simulated right here in Space Engine is actually the thin disk of a typical spiral galaxy. But most of the galactic mass is actually in the so-called galactic halo, which is more or less invisible because for the most part we think it contains a lot of dark matter, but also some stars and globular clusters. It also contains a lot of so-called stellar streams, which are normally the leftovers from various galactic collisions. And we've seen these stellar streams not just in the Milky Way but also around other galaxies as well, which obviously suggests to scientists that this is kind of how most of the galaxies usually evolve and develop this unusual shape. But then there's also something known as the thick disk. Now, we don't really know if all galaxies or if most galaxies have this. We know that ours does, but this thick disk is also a result of a relatively ancient actually, galactic collision. Now, the only thing we know about this galactic collision is that it was relatively large and resulted in a very massive thick disk. And it's also something that happened over 10 billion years ago, so this is a really ancient event. So most of the stars located in this so-called thick disk are also really old and really ancient. And most of the stars in this region actually orbit around the galaxy in a more peculiar way. Basically, they are usually more inclined to the galactic plane, moving above and also below the so-called galactic disk. And in some cases, they even go beyond that. So it's no surprise that at some point we were going to discover at least one star in this so-called thick disk that also contained a planet. And this is just one of these stars we've discovered. And so let's try to simulate what exactly the scientists discovered. So first of all, the star itself is not really that weird, only the orbit of the star is a little bit strange. This star is known as LHS 1185, and it's a very quiet and also relatively old, probably more than 10 billion years old, M-type star, or in other words, a red dwarf, very similar to the nearby Proxima Centauri. The motion of this star around the galaxy means that it actually goes above and then below the galactic plane by roughly around 6,000 light years. And just to give you something to compare this to, the distance between the center and our sun is about 27,000, so it basically goes all the way to the edge of the thin disk, back and forth. And we've seen quite a lot of stars doing this, but this star is the first one we've discovered with an actual planet around it. And we honestly didn't think that any of these stars could have such planets, mostly because a lot of these stars are really ancient, so their metallicity, or basically their composition, is very different from our own solar system. Most of these stars, they only have hydrogen and helium. They don't actually have a lot of silicates, a lot of metals. They don't really have anything to make terrestrial planets out of. But this star has a planet that's very similar in size to planet Earth. This unusual terrestrial planet known as LHS 1815b seems to be really extreme in many different ways. First of all, it orbits really close to the parent star, so the single orbit here takes about 3.8 days, meaning that it's very likely tidally locked. It's also probably one of these so-called eyeball planets, with the star-facing side being extremely hot and the opposite side being relatively cold or possibly even extremely cold. But the most unusual part about this particular planet is that it seems to be terrestrial and extremely dense. So here, let me put Earth for comparison. As you can see, their size is relatively similar. This is only about 8% larger, but it has about 8.7 times more mass, meaning that this is a really condensed object. The surface gravity here is probably about 7.4 times higher, meaning that you would basically weigh 7 times more on this planet than you would on Earth. Probably not the best planet to go to if you want to lose some weight. But jokes aside though, this is really a very unusual object. Its density is technically higher than density of metals here on the planet. This can only suggest that this planet is probably made up of some really exotic minerals and metals, something that might not even exist in the solar system, or at least something that we've never seen before. And because this planet is so close to its parent star, it very likely does not have water or ice or really anything on the surface. And depending on its composition, it could be one of the more exotic planets we've discovered so far. We've actually never seen a planet that's so extremely dense, yet at the same time being so close to its parent star, while also being one of the more ancient planets and stars we've discovered in around our neighborhood. Simply because this is actually not so far away from us. It's only about 97 light years away, which is comparably close compared to other exoplanets we've discovered. And considering that some of the more dense objects in the solar system are usually metallic asteroids, where density can be up to about 8 grams per centimeter cube, and our planet Earth being about 5.5 grams per centimeter cube on average, this here is really strange, because the density here is about 37 grams per centimeter cube. And just to give you another comparison, this right here is known as osmium, and this is the densest metal we know. Its density is about 22 grams per centimeter cube. So still dramatically lower than what we've discovered on this planet. In other words, there's quite a lot of mysteries to resolve here. And the biggest mystery is of course the origin of this planet so close to its parent star. One of the possible resolutions to this mystery is that maybe this planet was actually born a little bit differently. Maybe this used to be some kind of a gas planet. In other words, a planet similar to, for example, Jupiter, that actually had a solid core that eventually, with time, got compressed and became extremely dense. But as it came closer and closer to its star, all of the gas evaporated, eventually leaving behind the extremely dense core that's now there, orbiting as a typical terrestrial planet. We actually even have a name for such planets. We usually refer to them as Chtonian planets, basically planets that are the remainders of scorched giants, or other gas-like objects that eventually lost all of their gas due to the proximity to the star. Now obviously there is currently no way for us to test any of this, but there are definitely a lot of questions that need to be answered about this unusual star system. So overall this is definitely one of the more interesting discoveries of the past few months, and will most likely result in some really interesting follow-up papers that might discover something else about the system that we currently don't really know just yet. On that note though, that's kind of all I wanted to mention. It's a very interesting star orbiting in a very peculiar way with an extremely unusual planet that seems to be, at least currently, difficult to explain. An extremely dense planet in a very peculiar system. Hello wonderful person, this is Anton, and in this video we're going to be answering the question of how Milky Way galaxy formed. We're going to, I guess in some sense, reverse engineer it using one of the recent studies. Modern astronomers were able to find the answers to a lot of different questions. For example, today we have a pretty good understanding how planets form, how star systems form, even how our own moon formed. However, when it comes to the formation of galaxies, and specifically the formation of our own Milky Way, there's very limited data. This is actually one of the few simulations created by the Caltech approximately 5 years ago, where they simulated a potential way the Milky Way galaxy was created from very smaller dwarf galaxies. This is over a period of approximately 13.8 billion years. And here you'll see that the shape will start forming relatively soon, and you'll see the familiar disk shape as well. Now, this is not exactly satisfactory though, because it doesn't really use any observation of the galactic formations and also galactic shapes and stars and globular clusters we already have in the universe. So this is why The scientist who wrote this paper, that you can find it in the description below, decided to do just that. He decided to focus on what we actually see and what we know and try to reverse engineer of how it may have appeared there. But how could you possibly reverse engineer a galaxy, especially from within the galaxy itself? What could you possibly use to try to, I guess in some sense, guesstimate, or in this case scientifically guesstimate, what and how some of the parts were combined here? Well, if you look really closely, and especially if you increase the amount of stars visible to us, you might notice that there are actually a lot of really bright objects located in the so-called halo of the galaxy, essentially the area around the galaxy, not in the disk itself. If I come a little bit closer, you'll see them even better. And there's actually a lot of them, there's hundreds of them. These objects are known as globular clusters. Here's one of many of these clusters available in our galaxy. Now, as the name suggests, these are clusters of basically stars stuck together and orbiting the galaxy in one way or another. But for the most part, most of these globular clusters, or at least the vast majority of them, do have very peculiar orbits, which of course for many years suggested to scientists that they probably came from other galaxies, or they were probably formed in some very mysterious ways. And so by using globular clusters, the scientist behind this paper was actually able to relatively accurately predict where some of these globular clusters came from, and how all of this then sort of resulted in the formation of our own galaxy. And all of this is of course based on the idea that the Milky Way had a very violent past. It very likely absorbed a lot of different galaxies, possibly hundreds if not thousands of smaller galaxies, and all of them together created the shape we know as Milky Way today. But there are only some of the larger ones we can sort of predict and see. In other words, some of the smaller galaxies that the Milky Way absorbed probably disappeared forever. We'll never really be able to tell that they even used to be there. Now here's the picture of actual globular cluster. This is M80 that you can see from, I believe it's Scorpius constellation, and it's about 80,000 light years away from us. And for many years, scientists have always speculated that the globular clusters are actually the leftovers of these dwarf galaxies that combine to form larger galaxies. One of the best examples of this is from the very well-known Sombrero galaxy. This is one of the most beautiful and also one of the easiest to see galaxies out there. And even though it sort of looks really calm, like nothing is happening here, there are thousands of globular clusters, and very recently scientists even discovered that this is a result of major collisions that happened in the past. Way more than collisions that happen in the Milky Way. So essentially, the number of globular clusters in some sense suggests the number of collisions the galaxy may have experienced, especially the globular clusters that have peculiar orbits that are not aligned with the plane of the actual galaxy. We've also seen a lot of globular clusters and individual stars connected to these so-called stellar streams, and we know that these are also the leftovers from various dwarf galaxies that were sort of slowly stripped away by the Milky Way's gravitational power. So all of this evidence suggests that globular clusters are directly related to the potential dwarf galaxies that the Milky Way is made from. These are basically kind of like the Lego blocks that we can then try to use to analyze what collided with what to create our galaxy. And so the scientists behind this paper discovered that from the approximately 76 various globular clusters that he was able to analyze, all of them could technically be qualified as 5 to 6 different collisions, major collisions. In other words, our galaxy may have experienced 5 to maybe 6 different very specific and very major collisions that then created the shape that we know today. And the first such collision happened between the early Milky Way and a relatively massive, probably the most massive dwarf galaxy known as Gaia Enceladus, more unofficially known as Gaia Sausage. So Gaia Sausage is actually something we've discovered not so long ago, and we even were able to identify what seemed to have been its core, basically the actual nucleus of this galaxy. This is the globular cluster known as NGC 2808. And so a lot of these clusters may have actually been the centers of these smaller galaxies and now are kind of left there orbiting around the Milky Way. This collision very likely happened approximately 11 to maybe 10 billion years ago, and so this was one of the first major additions of mass and different gas and of course stars to our galaxy. It's possible that after this period there were a few smaller collisions, but nothing really that major for at least a billion years. About a billion years later, the next collision happened between the so-called Sequoia galaxy, or FSR 1758. Today this galaxy is extremely difficult to see and it's basically covered by dust. We've actually discovered it by accident like so many other things. but it also introduced a lot of matter, a lot of stars, and a lot of different globular clusters that are still found in our galaxy. This followed by another galaxy known as Sagittarius Dwarf Galaxy. This is a galaxy I've briefly talked about in one of the previous videos, and the so-called Sagittarius Dwarf Galaxy that we also discovered not so long ago is also responsible for making the Milky Way sort of rippled and wobble a little bit. I've talked about this in one of the previous videos. So in other words, all of these galaxies that collide with the Milky Way, their leftovers are still there, still kind of causing a lot of different disruptions, while at the same time changing the shape of our galaxy even today. The fourth galaxy is unfortunately actually invisible, as in it's probably not there anymore, or maybe it existed a long time ago and just disappeared, or it's really difficult to see. But the scientist behind this paper, because he's Australian, decided to name it Koala. And the reason why he decided to name it Koala is because, according to him, this galaxy was moving really slow, and so all of its stars and all of its globular clusters ended up orbiting in a relatively similar sort of orbit as the rest of the globular clusters and stars that existed in the Milky Way. Now, we're not entirely sure what happened to the galaxy afterwards, but it could have been completely absorbed by the Milky Way's disk. And the last collisions and the last globular clusters are represented by the so-called Helmi Streams, which are just some of the many different stellar streams that exist around our galaxy, representing the basically stretched and disrupted galactic shapes that no longer exist, but used to be in orbit around the Milky Way. Now eventually this all will settle and create the shape that's familiar to us, but for now, as you can see, this is all really chaotic. And as a matter of fact, all of the assumptions that the scientists had about these events, and some of the assumptions actually do agree with other scientists as well, is that all of these events happened relatively early, about 8 to 11 billion years ago. And then eventually, the galaxy had at least 7 billion years to stabilize its shape and create the disk that it has today. Now, there were actually a few more galactic clusters that were results of much more energetic collisions with smaller galaxies, and also a few more galactic clusters that he couldn't really attribute to anything, but for the most part, these 5 major collisions were quite easily attributed to these 5 specific events. And this would definitely explain not only how our galaxy became so massive and so large, but also explain the existence of a lot of other shapes in our galaxy, including of course the stellar streams, the very difficult to see dwarf galaxies, and the multitude of other objects we've discovered around the Milky Way in the past few decades. So there's actually a lot of stuff orbiting the Milky Way, and most of it, if not all of it, is a result of a collision between a smaller galaxy and the Milky Way that essentially absorbed what seems to be like a few dozen or possibly even a few hundred different galaxies. And today we know that it's far from being done. A lot of other galaxies, including Large Magellanic Cloud and Small Magellanic Cloud, have already slowly started being absorbed by the Milky Way. We've actually detected streams coming into the Milky Way from these two galaxies, and it seems that in a few billion years they will be also gone and leave nothing but a few globular clusters behind. And the other major discovery from this paper is the estimate on how much mass and how many globular clusters were probably acquired during these early collisions. And it seems that even though possibly only about 1 billion stars remain in the Milky Way from these early collisions, overall it seems to have acquired most of the globular clusters. And it also suggests that maybe the globular clusters are actually one of the few actual objects that can remain for many billions of years completely intact and not fall apart, even following a major galactic collision. So this could be a tool that we can use in the future to discover more about other galaxies out there. But not all galactic clusters were captured. At least 11 that he identified were actually made in the Milky Way. This means that one day we could actually even establish how many globular clusters a galaxy is supposed to have, and then by using the number of galactic clusters, try to estimate how many galaxies were absorbed in the process of forming a certain galaxy. Hello wonderful person, this is Anton, and in this video we're going to be talking about a very recent release of a tremendous amount of data from the so-called Project Breakthrough Listen. This is our attempt at finding extraterrestrial intelligence out there, and in this video you're going to discover what we found out. Although I don't really want to disappoint you because we haven't really found much. However, there is some good news coming out of this. The wonderful project known as Breakthrough Listen is one of the biggest attempts humanity has ever undertaken in trying to discover extraterrestrial intelligence. It's essentially based on obviously listening for various radio frequencies out there in outer space and trying to identify something that might appear artificial or extraterrestrial. Or actually not just extraterrestrial or artificial, it also has to appear as if it was created by some sort of intelligence somewhere out there. And in the last few years, the Project Breakthrough Listen has now become the major observation system for trying to detect extraterrestrial intelligence in outer space. And all of this mostly is because it's privately funded, specifically by the Russian-born American entrepreneur Yuri Milner and his wife Julia. Milner has already put in around $100 million or so in trying to establish an effective system for humans to look for extraterrestrial intelligence, or once and for all settle the question of, are we alone? Yes, we are. But anyway, so that's the project in a nutshell. You can learn more about it in the description below. But now they've also released one of the major new updates, and it's completely open for everyone to access. The website that I posted in the description has this link to open data, and the recent release of open data includes roughly around 2 petabytes, which is equivalent to about 2,000 terabytes of data that has not really been processed yet. In other words, it's the data collected by listening to the center of the galaxy, and some of it might contain the messages from extraterrestrial intelligence. But we don't really know if anyone is talking to us because it hasn't been processed. Which is why the Foundation decided to make it open so that anyone can go and try to look for it themselves. And although you do need a little bit of training to try to figure this out, it's absolutely possible to do this yourself without any actual formal training in any university. In other words, there are already a lot of so-called citizen scientists doing this in their free time by using the resources available right here from Berkeley University, Berkeley City specifically, and by then essentially getting all of their data from the form itself available through the website in the description. And this specific galactic survey, as you would call it, focused on one specific area where we think we'll have the highest chance of discovering something. The so-called galactic center. Basically the area with the highest density of stars and everything else for that matter, and the area where there might be something going on and someone communicating. This idea is especially based on these so-called Schelling points or focal points originally proposed by the very famous Thomas Schelling, who was famous for developing a lot of game theories and a lot of economics related theories as well. And one of them was in regards to the so-called focal points, although now we usually refer to them as Schelling points named after him. So what this refers to is to the idea of various alien species being out there but being unable to communicate with us. And if you can communicate with someone and you cannot actually see them, you have to find a way to strategize in order for you to come up with a potential way to communicate or potential way of doing things together without true communication. The way he actually explained it is by using various Cold War analogies and also by essentially integrating various game theories ideas into trying to understand how people, and in this sense aliens as well, would actually do things without being able to communicate. So, for example, let's just say we would like to find a way to communicate with someone we cannot see. We thus need to come up with a strategy where we know that they will do very similar things to what we'll do. So for example, since we communicate with radio waves, we can make an assumption that some kind of an alien super intelligent species will also be using radio waves for communication, at least to some extent. This is one of the possible Schelling points. The other point we can make out of this is that there has to be an area somewhere out there in a galaxy where all of the intelligent species will try to kind of connect with one another. Think of it as a kind of a marketplace where everyone comes in and is then able to do all kinds of things like trade and so on. Now, where would this area be? Well, if we apply Schilling's theories, this area should be right in the center of our galaxy, or somewhere in the vicinity of the center where it's relatively safe for people and aliens and various species to survive and not be destroyed by radiation. And since this area is also very rich in energy and there's a lot of potential for harvesting energy for other resources and also just for communication in general, this would be a perfect location for conducting extraterrestrial business, or at least to make new friends. Now, in this case, we don't think there's an actual market there, but there might be beacons of communication, sending out signals, sending out all kinds of different messages, possibly even different types of guidance. So we expect to see something there, assuming other aliens act and sort of think in the same way as we do. Which is why Project Breakthrough Listen did just that. They listened to the center of the galaxy for just a few years, I guess, and they decided to produce all of this data and make it available for anyone willing to analyze it. Mostly because there is a lot of data and just not enough researchers doing it. And remember, in the last few years, citizen science has become really advanced. There are actually a lot of different amateur scientists, amateur astronomers finding out things that other scientists were not able to find. Like, for example, the second ever interstellar comet, the so-called Comet Borisov, was also found by an amateur scientist. And even the famous dim Tabby star was technically discovered by citizen scientists as well. It became prominent once the researcher picked it up and actually started analyzing it, but it was originally discovered by amateur astronomers. And although previous analysis only focused on 1 to 4 GHz, now we have data going all the way to 12 GHz of radio communication, allowing more different frequencies to be analyzed for potential communication. Now this is kind of what we use here on Earth as well. These are very common frequencies for satellites, for example. Also, as you probably know, your Wi-Fi works at 2.4 to 5 GHz range, so all of these frequencies are technically what we would call Schelling points as well. But even though the main purpose is to find aliens or alien communication, this data can also be used to find different anomalies that might be out there and could help us explain phenomena we don't really understand just yet. For example, FRBs, fast radio bursts. And what's really interesting here is that up until I guess about 5 to 10 years ago, we had the opposite problem. We had a lot of people interested in SETI. SETI was actually really popular. I had it running on several computers trying to analyze data as well. But as time went on, we kind of reversed the situation. Now we have a lot of data coming in, but unfortunately not enough people interested in analyzing the data, or just not enough researchers interested in the idea of looking for extraterrestrial intelligence to begin with. And honestly, I think it's because of the TV show known as X-Files that was very popular approximately 20 years ago, and then as the TV show sort of disappeared, so did the interest. Nevertheless, because the data is freely available, I expect a lot of people to join in at some point, and we already have several papers coming out even within only a few days after the data was released. And interestingly, well, right now we haven't really found anything. This particular study you can find in the description below as well, analyzed the stars located in the so-called Earth Transit Zone. Essentially, these are the stars that would be able to see Earth transiting in front of the Sun, which would allow aliens to see our planet Earth in the same way that we see other exoplanets and discover them using telescopes like Kepler. And by analyzing frequencies between about 3 to about 8 GHz, they've unfortunately identified only one potential candidate for some sort of a communication that could have been from aliens. But upon further analysis, it turns out it was from an Earth-based satellite and not from aliens. In other words, nothing was discovered from this particular study, and unfortunately we'll have to keep looking. And one of the main reasons why Earth Transit Zone is so important for us in looking for potential extraterrestrial communication is because of, once again, these so-called Schelling points. This is literally what we're doing here on Earth. We're looking for these exoplanets and then trying to see if anyone is talking to us. And so if aliens are doing the same, and are actually thinking the same way we are, they would also be trying to communicate with potential planets that they can see transiting in front of their stars. And so unfortunately, as of today, none of the breakthrough listen data has discovered anything, but we've only scratched the surface here. We've only analyzed a very small amount of frequencies and stars. With such a tremendous amount of data that's been released though, there's a lot of things we can still discover, even if it's not aliens. We could still maybe discover some unusual phenomenon we've never really known about before. And the good news is that SETI itself is also adding a lot of new components to various available telescopes, which will allow us to collect even more data during regular observation missions. So in the next 5 to 10 years, we'll be able to collect so much data that we'll definitely need a lot more researchers or even amateur scientists like you, possibly looking through data and trying to discover something out there. And just like with so many things in science, this could be discovered by a completely regular person using the data that's openly available. In other words, this could definitely be you. Hello wonderful person, this is Anton, and in this video we're going to be talking about this really small galaxy that you see on the screen with the Milky Way right there in the background. And in this video we're going to be talking about something new that was discovered by the scientists in regards to the Milky Way itself and how this tiny galaxy known as Sagittarius dwarf seems to influence the creation in the Milky Way. When it comes to galaxies, for the most part, what we see, the visual components of the galaxies, these are obviously stars. And the creation of the stars, for the most part, is still kind of being investigated even today. Now we know that in our own galaxy, the Milky Way, currently there's roughly around 1.5 masses of the Sun being used to generate new stars. Now, if you were to kind of try to calculate the age of the galaxy and then multiply this by the number of stars per year, you would not actually get enough. There would only be about 10 to maybe 15 billion stars created. But we know that our galaxy is way bigger. There are a lot more stars here, possibly up to 400 billion stars, suggesting that something major must have happened to create most of them. And so, by looking around the night skies, scientists have identified several cases of what's known as starburst galaxies. These other galaxies out there where stars are being generated really fast and create these extremely beautiful and very bright environments where basically everything is being generated all at once, suggesting that this is exactly how Milky Way must have created its stars as well. At the same time, even though we kind of see these starbursts happening everywhere, we're not entirely sure how they start. But we've always believed that most of these starbursts begin with some sort of a major collision between a larger galaxy and possibly a smaller dwarf galaxy. And this does seem to be a case for many of the galaxies we've discovered so far. A lot of them seem to be going through the merger between two galaxies, but not always. At the same time, when the beautiful Gaia Telescope that you see right here started to look around and trace very specific motions of nearby stars, and essentially creating an extremely detailed map of nearby stars, up to about 2 billion stars actually, we were able to then also identify some of the age groups and connect them all together. And today, based on this observation, we know that there were at least 3 major times when these stars were generated in the last 6 billion years. There was a major stage right here, this is when starburst occurred, and this is very likely when the sun was born as well. Another one about 2 billion years ago, and then another one somewhere around 500 million years ago. All 3 stages were so-called starburst stages when the vast majority of stars were generated, during which the Milky Way probably looked something like this for at least some time. And it seems to have happened everywhere in the galaxy, not just in the middle, for example, if this was related to some kind of a black hole activity. So because this was an entire galaxy doing this, something else must have occurred for all of the starbursts to kind of be initiated across the entire galaxy. And so we've always had some ideas here and there, and also a lot of different explanations and theories on what could have started these starburst events, but nothing really concrete so far. Until, I guess, this paper that will be published relatively soon, and you can also find in the description below. And the paper itself is basically focusing on something entirely different. Not really on a galactic collision as much, but on the galactic interaction. And more specifically on the interaction between Milky Way and this galaxy right here, known as Dwarf Sagittarius. Now, you may have never heard of this galaxy before, and honestly I wouldn't really blame you because we didn't really know much about it. Located in the so-called local group of galaxies, which basically includes our neighbors, the Triangulum and the Andromeda galaxies, it wasn't really until recently that we were finally able to identify it as an actual galaxy out there, and not just any kind of galaxy, a relatively massive, although difficult to see galaxy. You can see that it's somewhere right here in this image, and one of the best known members of this galaxy is actually this right here. This is a globular cluster known as M54 or Messier 54, which is one of the more well-known globular clusters and is also very likely the core of this galaxy. Basically, this is probably where the central black hole for this galaxy is located as well. But because this galaxy is really massive, yet doesn't really have that many stars, it only suggests one thing. It has a lot of dark matter hiding on the inside. And we know that in the last few million years, it also seems to have influenced the shape of Milky Way as well because of its unusual mass. Today we believe that some of the ripples and some of the actual warps around the Milky Way were very likely caused by the interactions between the Milky Way and Sagittarius dwarf galaxy, and more specifically because of the way it orbits around the Milky Way in the polar region of the galaxy. In other words, it doesn't orbit along the disk, it seems to actually pass through the disk once in a while. But what does any of this have to do with the starbursts? Well, it seems that when the scientists behind the study looked at the orbital parameters and orbital passages of Sagittarius dwarf around the Milky Way, and then compared them to the starburst activities in the Milky Way, they seem to have found an exact correlation. And more specifically, the direct correlation between the closest approach of dwarf Sagittarius A to the Milky Way and the sudden formation of stars in our galaxy, which happened at least 3 times right here. And also, what's interesting is that they discovered that there's another 4th time happening right now, and it began about 70 million years ago. which of course corresponds to the closest approach of Sagittarius dwarf galaxy once again. In other words, if we were to try to emulate all of this, it would probably look something like this. Here we have a very simple model of Sagittarius dwarf galaxy passing through a simple model of the Milky Way, and as it does so, it's going to initiate the so-called starburst activity, although we're not going to be able to create this in this particular simulation. But basically, every time it passes close to the Milky Way, that's when the scientists behind this paper believe the starburst activity begins, with the most recent one having begun approximately 70 million years ago. Which is of course an excellent way for us to explain why the Milky Way galaxy had these specific, very unique starburst events that did not really correlate with any galactic collisions. So in other words, instead of swallowing a galaxy, it's very likely that the Milky Way had its starburst activities begin every time when the Sagittarius dwarf galaxy approached closer to its central disk. And notice here that after a few billion years of the simulation running, we're also going to form these unusual formations, almost like a ring-like shape or a star ring shape that you can kind of see right here. It's very, very difficult to see them, but the thing is, we've detected quite a lot of these as well. These are called stellar streams, and we've been finding more and more of these around the Milky Way in the last 10 years or so. So this is also one of the more recent discoveries, along with, of course, Sagittarius dwarf galaxy. Now, if I run the simulation long enough, eventually what's going to be left behind, apart from the stellar streams, is obviously going to be a relatively small core of the original galaxy, with something really small resembling a globular cluster similar to the one I showed you previously. And in the middle of this globular cluster is going to be a relatively massive central black hole. So today, a lot of scientists do believe that Sagittarius dwarf galaxy probably has one of the larger central black holes orbiting around the Milky Way, along with a lot of dark matter, of course, which is why it has so much effect on the Milky Way. And it also seems to be one of the bigger influencers when it comes to the galactic evolution of the Milky Way itself, something that we didn't really expect from such a small and relatively difficult to see galaxy. Now, this is of course something we need to confirm first, but it does seem like this galaxy has a lot of influence on the Milky Way, a lot more than we originally expected. So I'm pretty sure that some of the future studies will be focusing on this even more, mostly because this is quite an interesting, quite a mysterious object. We obviously have no idea what it looked like before, but it was probably a lot more massive and a lot more beautiful than it is today. And it's also very likely that most of its stars were actually absorbed by the Milky Way, and a lot of its mass is now part of our galaxy as well. But this also means that some of the stars in the Milky Way probably came from here, and finding them would be really interesting as well. Now, unfortunately, that's kind of all we learned from the study, but nevertheless, it's a pretty incredible discovery, and definitely something that needs to be confirmed as soon as possible, mostly because it would mean that our own Milky Way galaxy possibly did not have exactly the same evolution as some of the other galaxies. It has experienced galactic collisions and probably had some of the stars created that way, but this study seems to suggest that most of the stars in the galaxy were probably created as a result of an interaction between Milky Way and a much smaller dwarf galaxy, which is not something we expected to find. And this of course raises a lot of other questions, like for example, what about other galaxies that we have orbiting around us? What was their influence on the Milky Way? This is definitely something that needs to be investigated, and something that will probably create a lot of interesting studies in the next few years. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of a very strange white dwarf star. The star that didn't really make sense until the scientists tried to explain its origins. And I wanted to start our adventure today right here on Earth, but also by looking in the night skies and seeing one of the brightest stars in the night skies, which is Sirius A. It's actually right there, this is the bright white star you see. But the thing is, what a lot of people don't realize is that it's actually not one but two stars, and its partner is extremely small and very dim. In order for us to actually try to discern the partner, we have to start zooming into this star, as if we had a telescope and wanted to see what's up there in this region. And so here, once I start zooming in, and actually this right here is a globular cluster known as Gaia, you'll start discerning another shape somewhere near it, and there you go. So this is the partners Sirius A and Sirius B. And Sirius B is essentially the closest white dwarf star to us. And the reason why it's interesting is because it's somewhat similar to what we just discovered, although the white dwarf we just found is actually even weirder. So if I were to jump to Sirius B right now, this is kind of what it would look like. This is a star that's really bright, but is no longer technically a star. This is what's known as a remnant. And furthermore, this is technically the core of the star that used to exist in this region, and the total size of this object is approximately same size as our planet Earth. But the mass of the object is very close to our Sun, actually approximately 2% more massive than our Sun. So imagine this really dense, really massive object with a relatively small size. Now, because this is the remnant of the star, it doesn't actually have any nuclear reaction on the inside, and all of the heat produced is essentially the leftovers from when this used to be a star, so it's technically really slowly cooling down. And at some point it's actually going to even start changing its colors, first becoming a little bit more like the typical Sun today, and eventually becoming dimmer and dimmer, and then even turning into an object known as the black dwarf. Although all of this we expect to happen in like trillions of years from today. But anyway, enough about what white dwarfs are. There are other videos I made previously that explain this in a little bit more detail. Why are we really talking about this specific white dwarf? Well, it just so happens that very recently the scientists discovered an extremely strange white dwarf somewhere out there that was actually behaving really strangely and had very strange properties. Now, you might already know that our Sun is one day going to become one as well, very similar to this one. And the thing is, most of the white dwarfs we've discovered so far are usually approximately half to maybe 70% the mass of the Sun. Almost none of them are heavier than that. And Sirius B is one of the few exceptions we've seen so far that seems to have a massive white dwarf. But except for the much more massive size, it doesn't really have anything more unusual about it. And the other thing you have to be aware of is that when it comes to white dwarfs, they do have a limit of their mass. If they actually gain a little bit more mass, and here we can demonstrate this with Sirius B, you can see as soon as I give it a little bit more mass, it actually does sort of decrease in size, it becomes more dense. There's going to be a limit that it reaches where it can no longer sustain itself. It basically collapses and explodes. This limit is known as the Chandrasekhar limit, and as you can see, as soon as the white dwarf hits about 1.4 masses of the Sun, it instantly explodes as a supernova, and this is what we call Type 1 supernova, Type 1a supernova to be more specifically. And these supernovae are almost always exactly the same. They have very similar brightness. So this is why a lot of scientists today use these supernovae as a kind of a measurement device. Because their brightness is usually the same, we can use them to establish distances across the universe. And very often this Chandrasekhar limit or the supernova happen when two white dwarfs collide. So for example, if there were two progenitor stars and both of them eventually became white dwarfs, and then at some point they come too close together, they will also produce a supernova very similar to what you've just seen. But it seems that sometimes something else might occur. It appears that sometimes white dwarfs can actually survive the collision and create something a little bit more intriguing. So in this case, as you can see from this image created by Mohamed Naou for his research, the typical white dwarf has this structure. It has a lot of carbon and oxygen on the inside. It also has a helium shell and a hydrogen shell. And carbon and oxygen is here because most of these stars that produce white dwarfs are not massive enough to turn carbon and oxygen into fuel. If, however, a star is a little bit more massive, it can usually create fuel out of carbon, nitrogen, and oxygen and keep going a little bit longer. But our Sun and also some other stars cannot really do that, and so all of the white dwarfs they produce have this very similar structure. This white dwarf, however, doesn't seem to have this, and for some reason you can actually see its carbon pretty easily. In other words, it's not inside, it's on the outside. And the surface of this white dwarf seems to have a lot of carbon with some hydrogen as well, so this is a very strange mixture we've never really seen before. At the same time, its mass is about double the mass, meaning that it's about 1.14 masses of the Sun, not so far off from the so-called Chandrasekhar limit. And it also seems to move a little bit too fast across the night skies, which is actually how the scientists discovered it to begin with. They were using the data from the beautiful Gaia Telescope that has been collecting the motion data for all of the stars in the nearby space, and it already has data of approximately 1.2 billion different stars. And so by seeing this unusual motion across the night skies, they noticed that there was a white dwarf that was moving a little bit faster, about 120 kilometers per second faster. And this is also one of the fastest white dwarfs moving across the night skies right now. And it was more massive and had this very unusual chemical structure. And so when scientists tried to understand how all of this could have occurred, only one possible solution could explain all of these observations. The white dwarf was very likely a result of a collision between two white dwarfs, but instead of going supernova like you'll see here any second now, these two white dwarfs instead decided to collide into a single object. They did not produce Type 1a supernova, they instead produced an extremely interesting mix of two different white dwarfs. They instead mixed their cores, throwing off a lot of other materials, and basically ended up being one single object moving really fast across the night skies. Obviously their mass increased as well, and this would make sense because the mass that we're observing is about double the mass of a typical white dwarf. And because of this observation and also because of this analysis, this also suggests that what we're looking at is one of the older stars in our galaxy. Because this is what we think may have happened. The original system was probably very similar to the nearby Alpha Centauri, where there are two sun-like stars. Now here I put them on a very close orbit, but in reality they were actually on a really far away orbit, probably at least a few astronomical units away from one another. And eventually one of these stars, probably the more massive star, started growing larger and became what's known as a supergiant. And just to give you a bit of a perspective, if our sun is right here, this is what our sun is going to be like later on in a few billion years. So this is what one of these stars became as well. But let's go back to our miniature model because it's a little bit easier to visualize here. Now eventually the smaller star will actually get kind of swallowed by the larger star and it will start orbiting inside its envelope. But this will not last very long because at some point the larger star will actually expel its outer shell. It will create what's known as a planetary nebula, a lot of which are some of the most beautiful objects in the night sky, and will then only leave behind the core, which is essentially the white dwarf. And after a few billion years, this is what the system might look like. We have the white dwarf that's left, and the smaller star that's still there but is about to enter its giant stage as well. So possibly within a few 100 million years, the second star will now start growing and do the same thing. It will actually cover the white dwarf, which will start orbiting inside of it, and slowly make its way toward the core of the other star. Eventually this star will also disappear, producing another beautiful planetary nebula in the process, and we end up in a system of binary dwarfs. And here they are close enough to start producing gravitational waves that will slowly take them closer and closer to one another. And eventually they'll basically be so close that they'll combine and turn into this unusual object. In the process they'll also very likely shift their velocity a lot, and this process might take anywhere from 1 to 2 billion years, and so the result product we're looking at is approximately 12 to maybe even 13 billion years old. In other words, this unusual, very strangely moving object is one of the first stars in our galaxy that is now a white dwarf and is going to be this for a very long time. But there are still a lot of questions about this unusual object, such as, for example, why did it not explode after all? And also, since it's only about 150 light years away from us, if it does explode one day, this is potentially one of those objects that could be somewhat dangerous to be close to, because the supernova here is close enough to cause detrimental effects to the atmosphere of our planet. In other words, this peculiar object produced by two different white dwarfs could be one of those objects we need to kind of look at closer. We need to investigate how exactly did it develop. Is it maybe still spinning really fast, so that's why it's not exploding? Does it still maybe have a chance to go supernova? And if so, what are the possible implications for our planet? Because normally some objects like neutron stars and certain white dwarfs do not go supernova if they spin really fast. But stars lose momentum with time and they actually do decrease their spin. And eventually if it starts spinning a lot slower, it might no longer be able to maintain its own mass and thus go supernova. So this peculiar object does actually create a lot of intriguing questions we need to try to answer. So trying to understand why this star failed to create a supernova is somewhat important for, I guess, in some sense, our own survival. And that's because there were actually several studies in the past that suggested certain supernova may have affected the climate and the atmosphere of our planet, and we've even seen signs of certain supernova here on the planet by looking at various layers of sediments here on the planet Earth. So in reality, it could be actually white dwarfs and not Betelgeuse that could create the next supernova that we might be able to see from Earth, but hopefully it's not close enough for us to worry about. And here's, by the way, what might happen if one day a white dwarf, such as for example a Sirius B, goes supernova nearby. It might actually affect our atmosphere and create somewhat uninhabitable conditions on planet Earth. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery about our own galaxy. And it's something to do with its shape. Because it turns out that not only is our galaxy kind of warped, but it's also sort of wobbling. So about a year ago, or maybe a little bit longer than that, I made a video about this new confirmation from Polish astronomers who discovered that our galaxy was after all quite warped. This is something scientists suspected since early 1950s, but obviously because of our location in the galaxy, basically being within it, it's kind of difficult to see what the shape really is. And generally speaking, most galaxies out there are not actually warped. A lot of them are relatively flat and do have a somewhat disc-like shape. And so the fact that our own galaxy is not really that flat is actually a little bit unusual. And so for many years now, scientists have been wondering why exactly does it actually have this unusual warp shape, and wanted to actually once again confirm if the shape is warped after all. And though the previous studies usually relied on observations from a much simpler telescope, this time the scientists were able to use one of the most complex observations of star motion across the night skies created by this beautiful telescope you see right here, Gaia Telescope. In the last few years, Gaia was able to collect the motion data for approximately 1.7 billion different stars around our solar system. And this data is only growing larger and larger. The next data release is actually going to be sometime in 2020, and the one after that is going to be in 2021. And so we're going to get even more star data available to scientists around the world to study various galactic phenomena. So Gaia Telescope is really a game changer here. And so the scientists who published the paper you can find in the description below did just that. They used approximately 12 million different stars from the Gaia database to determine that not only was our galaxy warped, and that the warp becomes really apparent at farther distances, approximately 50,000 light years away from the center, but that on top of that our galaxy was actually sort of wobbling around, similar to how a top spins when it's not exactly in plane. Now I think the best example I have of this is actually from the mind-blowing movie Inception, and if you've ever watched the movie you might remember that the top, spinning top, was supposed to represent if you're asleep or awake. So if the spinning top suddenly falls, it means that you're not sleeping, and if the top was actually spinning continuously, it meant that you were still asleep. But anyway, that's not really the point. The point here is look at how the top is spinning. It sort of wobbles as it rotates, but it doesn't really wobble for every rotation, it wobbles somewhat discontinuously. And interestingly, this is somewhat similar to what the scientists discovered Milky Way is doing as well. So it's not really wobbling once per rotation. For example, if this is a model of our galaxy, and let's just say somewhere here in the middle is going to be the solar system, it usually moves around the galaxy once every 220 million years. This is something we refer to as the galactic year, and you can check out more about this in one of the previous videos. But by measuring the data from the Gaia telescope, the scientists determined that a single wobble of the Milky Way takes around 600 to 700 million years. In other words, approximately 3 times as long as the single rotation around the galaxy of our Sun. It also doesn't appear to be static, and it seems to change over time as well. In other words, by looking at different parts of the galaxy, they were able to determine that it does seem to have a bit of variability. Nevertheless, this seems to be a lot faster than what the dark matter halo should be allowing the galaxy to do, because the halo itself moves much slower. And it's also a lot faster than the so-called magnetic field of the galaxy as well. So in other words, this wobble is still a lot faster than it should be moving. Which is why obviously it creates a lot of mysteries, such as, for example, so what exactly caused this, and how did this happen, and is it going to get even worse? And the initial explanations actually did involve either dark matter that might have essentially warped the galaxy by coming too close to the galactic plane, or possibly the effects of the magnetic field that may have shifted the stars and the gas around. Unfortunately, none of these explanations really showed us or explained how exactly this got to wobble so much, and why is it that it's changing over time. But there is one thing that helped us actually explain all of this, and it's very likely the reason for both the wobble and the unusual shape of the galaxy. And the actual culprit is the nearby dwarf galaxy known as Sagittarius Dwarf Galaxy. This is actually a barely visible galaxy that sort of orbits around the Milky Way, and this is kind of what it might look like if you were to look at it a little bit closer. And essentially what this galaxy used to be was obviously a much larger representative of the so-called orbiting dwarf galaxies. But as it orbited around the Milky Way in the last few billion years, it very likely lost a lot of its mass and a lot of its stars, mostly because the Milky Way galaxy is tidally disrupting it. But since its mass is actually really high, or potentially high, it also disrupted the Milky Way. And this disruption happened because this Sagittarius Dwarf Galaxy orbits in the so-called polar orbital plane. In other words, it actually crosses the galactic plane twice, and then sort of moves around this way. And in the last few years, we've even discovered several of these stellar streams, and one of them we've talked about very recently. And these stellar streams are essentially the leftovers of various interactions between smaller galaxies and our own Milky Way. Some of the previous studies established that it probably looks something like this, and it's about 1 million light years in length. And essentially, as Sagittarius dwarf galaxy orbits around the Milky Way, it's going to leave more and more stars in this stream and eventually fall apart completely, becoming part of the Milky Way. And today, what's left of this galaxy that's approximately 70,000 light years away from us are 4 large globular clusters and still a lot of dark matter and also a lot of really massive stars. And since it already passed Milky Way several times, it's very possible that it lost a huge amount of mass and a lot of stars already, meaning that it probably was much larger and much more massive when it kind of started orbiting around the Milky Way. Judging by its location in the night skies, the scientists think that it probably passed the galactic plane last about 300 to maybe 600 million years ago, and it's very likely going to pass through the galactic plane once again in about 100 million years from now. But the thing is, we're not entirely sure if it's even this galaxy that caused this. There are so many different dwarf galaxies orbiting around the Milky Way that in reality the warp itself could be actually the result of the interaction between several different dwarf galaxies and the galactic plane of the Milky Way. So until we get more data from Gaia Telescope and until we are able to analyze it a little bit better, we're not going to know for sure if it was the Sagittarius dwarf or some other galaxy, of which we have quite a lot to choose from, as you can see. But Sagittarius dwarf galaxy is actually really interesting because there were even papers suggesting that the reason why the Milky Way has its spiral shape to begin with is actually because of the interaction with this unusual galaxy. In other words, its mass and its total capacity to influence our galaxy is actually really high. And so it does seem to have a lot of effect on what's happening in the Milky Way and how it sort of evolves over time. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery coming from the center of our own galaxy, right where the black hole is. A new star that's a new record holder. So what you're looking at right here is a simulation of the previous record holder, the so-called fastest star in the galaxy. This is the star known as S2, and right around here at the closest approach of its orbit, it's able to reach the velocity of about 2.5% of the speed of light, or around 7,500 kilometers per second. And the scientists have quite extensively studied these so-called S objects, which are essentially stars, very compact stars, really close to the center of the galaxy. But very recently, the German scientists, whose paper you can find right here and also in the description below, discovered another star, another record holder for the fastest star in the galaxy, even faster than S2. The star, now known as S62, seems to have a very unusual orbit, very eccentric orbit as we usually say, which as you can see right here seems to be very different from any other object in this region. S62 takes approximately 9.9 years to go around Sagittarius A star, the central black hole, once, and as of today this is one of the more unusual stars we've discovered so far. Although this does not include the so-called G objects about which I've talked in the previous video from a few months ago. G objects are still the weirdest objects in this region, and you can learn more about these objects in one of the videos that's going to be popping up around the end of the video. But why is this called the fastest star? Well, it's because, once again, at the closest approach to the black hole, which is what we refer to as periapsis usually, the star itself moves at around 10% of the speed of light. That's about 30,000 kilometers per second. Just to give you a perspective here, the fastest man-made object, which is of course the Parker Solar Probe, is going to reach its highest velocity in 2024 when it's at the closest to the Sun. And so right here at the periapsis of its orbit, at the closest approach to the Sun, the maximum reached velocity is going to be, let's see in a few seconds here, so it says here approximately 190 kilometers per second. That's dramatically lower than the 30,000 kilometers per second that S62 has when it approaches Sagittarius A star, which is also about 4 times higher than the previous record holder S2. Now, why does it have such a high velocity? Well, it's of course because of the unusual elliptical orbit. When it comes to orbits, if I were to give Parker Solar Probe a more circular orbit, in other words, if I were to decrease its eccentricity from about 88% to, let's just say, 0, the velocity would now drop to about 139 kilometers per second. And so essentially, the orbital parameters always depend on the shape and the proximity to the object that is being orbited. So in this case, the eccentricity of the orbit of S62 is responsible for giving it such a tremendously high velocity. And I tried to kind of recreate this in Universe Sandbox by using a model of Sagittarius A star and just a star similar to our sun right here. And you'll notice that right around this area, the velocity is actually close to about 30,000 kilometers per second as well. And the closest approach here is equivalent to the distance of the Sun to, I guess, a little bit closer than Uranus. So in other words, maybe about 15 astronomical units or so. And this kind of a behavior and this kind of an orbit is very, very difficult to explain. So somehow this unusual star that's about 2.2 masses of the Sun was able to survive for a relatively long time in this region, and it doesn't seem to have any signs of being disrupted or being stretched or anything. It approaches the black hole really closely and then leaves really, really far for the next 9 years. The farthest distance here is probably around 1,000 astronomical units or so, and so most of the time the star spans away from the black hole and then for probably only a few months or even just a few weeks approaches this region right here and ends up moving really, really fast in this region. But we really can't explain how this star got this orbit. One of the main explanations right now is that it possibly had a partner, basically another star in orbit, and this partner somehow got kicked out of the system or possibly even swallowed by the black hole, and this of course left the main star with a very peculiar orbit. And because these two stars act on each other as they orbit around one another, if you were to remove one of the stars, the orbit of the other would change as well. And this is how we think maybe it acquired this unusual eccentric orbit. But to have this really extreme orbit, a lot of things need to happen, and the fact that this star did not fall into the black hole is a mystery. At the same time, in one of the previous videos, we've talked about how some stars can naturally form around black holes. It's quite possible that this is one of those stars that was formed in this orbit from all sorts of material that was left around the black hole in its accretion disk and also in its neighborhood. And this of course could have resulted in the production of several of these S objects. We currently refer to this region as the so-called S cluster, and for the most part we don't really know how these stars were created. The most prominent theory is that they were captured from other regions, but we don't really know, and they could have been just naturally created around the black hole. But hopefully by studying S62 in a little bit more detail, and by identifying specific features of this star that other stars might not have, we'll be able to answer the question of its origin. Now right now we don't actually even know what's going to happen to the star, but the chances for it to collide with something and probably even fall into the black hole are pretty high. What is, however, pretty interesting about S62 is that it appears to be very similar to other stars in this region. In other words, if we were to look at all of these S objects orbiting around the black hole, they all seem to possess very similar features. They do seem to be compact, they seem to have relatively similar brightness, and they do appear to be star-like, not like the G objects I've discussed previously. And so in some sense they probably do have similar origin, and discovering this will probably be quite a mystery to resolve. Now, one thing we need to understand is that even though the simulation makes this appear as regular space, nothing here in this region is regular. This is an extremely dense region. Here there's a lot of material, a lot of different energy, and the black hole itself creates very inhospitable conditions. Here the density is much higher, like thousands of times higher than the density of space where we are, and there's millions and millions times more energy and more very energetic events happening here on a regular basis. So it will be very difficult to imagine what's really going on here unless we do more thorough observations and try to simulate them here using supercomputers. But one thing we need to remember is that this region is extremely different from the space where we are. The actual density here is much higher, so there's like thousands if not millions of more particles in the actual space, and at some point some scientists even suggested that the region around the black hole is almost like some kind of an atmosphere. There's a lot of particles here that do interact. While at the same time this is also an extremely active and extremely energetic region. There's like millions and millions times more energy here. There's a lot of radiation, a lot of various stuff going on, and this is an extremely active environment. So in some sense, trying to imagine this from our perspective here, where the solar system is going to be really challenging. The only way we can probably imagine what's happening here is by simulating it using supercomputers, because it's very difficult to see that far. Now, one day we might be able to answer the question to all of the mysteries around the supermassive black hole, and one day we might be able to understand what's happening here. But discovering stars like S62 is a very important process of us getting to these answers. Now, why do we want to know these answers though? Well, one of the reasons is because, as I discussed in previous videos, we know that our black hole did erupt a few times, and some of these eruptions were really powerful. So if one day S62 decides to collide with our black hole, a huge amount of radiation is going to be released. And we need to understand if this is something we need to be worried about. If the so-called Fermi bubbles that we discovered a few years ago were actually formed by a star collision with a black hole, we kind of need to understand if this can happen again and if this is something humans might potentially not survive. So these studies are pretty important, and understanding what happens in space and how it affects us is also extremely important as well. Hello wonderful person, this is Anton, and in this video we're going to be talking about this unusual star system known as 49 Ceti, located about 190 years away from us in the constellation Cetus. And this star created another mystery we can't really explain. So first of all, what exactly is this star? Well, about 40 million years ago, a completely new star was made in this cluster right here, known as IC2391, or also known as Omicron Velorum cluster. But even though other stars that were created in this cluster seem to be relatively normal and appear as we expect them to appear, there is something really peculiar about 49 Ceti. Specifically, it seems to have a lot of gas in the actual star system that should have been gone from there a long time ago. Now, to try to understand what's going on here, we need to take a look at this illustration created by the National Science Foundation that kind of gives us the idea of what happens with stars when they just form. So basically, after a typical supernova or any other event that creates a large cloud of matter, eventually this cloud starts to coalesce into a larger piece and then ends up creating the new star system. This eventually, within a few million years, leads to a typical star system with planets in it, but this here is what we're interested in. This gas disk, also known as the protoplanetary disk, is something we're quite familiar with because we've seen so many out there in our own galaxy. And we usually expect all of this to disappear within a few million years as the star acquires its star status and starts emitting so much radiation that it pushes all of this gas out of the star system. While at the same time, prior to this, a lot of planets will develop and will create actual bodies of matter that will then turn into either terrestrial planets or gas planets. So essentially, this is the process by which we think all of the star systems are created. Yet 49 Ceti doesn't seem to meet this criteria. It seems to be doing its own thing and very different from what we expect it to be doing. So first of all, this beautiful star that's about 186 light years away from us is an A-type star. It's an extremely bright star, it has a lot of energy, it's about 9000 degrees Kelvin in temperature, it's also about 20 times brighter than our own sun, and spins really fast. The velocity on the equator here is about 200 kilometers per second. This high speed of rotation may even turn the star slightly more squished as opposed to being a sphere, so we don't exactly know what this causes, but it might have some effect on the star system. But when the scientists behind the paper that you can find in the description below looked at this star system in more detail and by using various other frequencies, they've discovered that this star system, even though it's about 40 million years old, still possesses exactly the same parameters as a typically newly created star system. It has a lot of gas still in orbit around the star that hasn't really been dissipated or turned into planetary objects. And although technically maybe planets are hiding inside this gas when we're just not seeing them, the amount of gas that is still present in the star system is really astonishing. It's sort of beyond any theoretical prediction and seems to have no current explanation, so we don't really know why it has so much gas left. Now normally by this time in the formation of the star, basically 40 million years later, we really expect it to look more like this. It should already have almost no gas in it, it should have a lot of planets orbiting, and especially a star like 49 Ceti, which is a very powerful A-type star with a lot of emissions. As a matter of fact, if we were to look at the procedurally generated star system 49 Ceti in Space Engine, which uses the current physics and current understanding of the universe, this is kind of what it looks like. You'll notice it has several planets, some of them are a little bit too close to the star is very bright and very powerful, and interestingly, there's even an unusual Neptune-like planet that orbits on its side and, according to Space Engine, possesses very simple single cellular life. Now all of this is procedurally generated, so it probably doesn't exist in real life, but nevertheless this is what we expect to see here after about 40 million years. We expect a multiplanetary system with a lot of development and possibly a lot of planets with moons as well. But once again, not exactly what we just saw. Instead, the observations revealed a huge amount of various gas, carbon monoxide, even hydrogen, and overall just a lot of dust. It still has a lot of material that's orbiting around the star, and all of this was seen in various different frequencies. And even though we've seen other planetary disks that do still possess some gas, and technically even our own solar system still has the asteroid belt and the Kuiper's belt that do possess certain particles left that could technically be seen in a similar way as we see here. Nevertheless, what we're seeing in 49 Ceti is about 10 times or even more so compared to every other star system we've seen so far. And what's even more unusual is that for the first time ever, we've actually seen the emissions from the so-called carbon-13, a much more rare isotope of typical carbon. We've actually never seen this in space ever. We know it exists, but there needs to be a huge amount of it for us to be able to detect it. So here, this was the first ever detection of carbon-13 emissions that are around 492 gigahertz. Once again implying that there is a lot of carbon gas that's still left in this star system. Now, there's really no definitive explanation to why this is so. I guess one explanation is that for some reason the system seems to be developing much slower than other star systems and is able to maintain the gas field and all of the carbon and hydrogen around it much longer than usual. But physically or theoretically, we don't really know how to explain it. One of the possible explanations is that all of this is caused by a lot of different collisions, specifically from things like comets. Cometary collisions could definitely generate signatures of carbon and a lot of other materials we're seeing, but there would need to be a tremendous amount of comets colliding pretty much constantly for millions of years for so much gas to be generated. Theoretically, we don't think it's actually possible. The other solution to this is that maybe instead of comets, there were actually quite a lot of various planetary collisions. Large planets colliding could produce the gas we're observing, but theoretically we don't actually think so many collisions can occur, and also normally planetary collisions should also be producing a lot of other effects, such as various infrared effects that should have been seen in this study. But we haven't really seen any signs of planetary collisions in this study, and there have been no other effects observed to suggest that this was a planetary collision of any kind. And so here we're back to not knowing what exactly is causing all of this gas to stay around the star system and why none of it has dissipated over time. So in that sense, it really creates this mystery that we can't currently explain. Which of course creates a major blunder for our theory of planetary formation. There might be a step missing here that we haven't really considered, and maybe 49 Ceti will actually explain to us what exactly is it that we don't really understand yet. Hello wonderful person, this is Anton, and in this video we're going to be returning to a very exciting exoplanet known as K18b. And in this video we're going to discuss a new study that proposes that it's very likely that this planet is a very interesting water world after all. And it even could be one of the most unusual habitable planets we've ever discovered. One of the most prolific space missions to date is of course the so-called Kepler mission. This was a two-part mission trying to find all kinds of exoplanets transiting in front of their stars. And as you can see from this simulation right here, it discovered a lot of different exoplanets out there, a lot of which have not even been confirmed yet, so there could be up to 10,000 different planets here. And one of these planets, or one of the systems with two different planets, is this right here. This is known as Kepler-218, or K218 for short. This was discovered during the second part of the mission when the telescope had a little bit of a problem, and there are actually two planets here, currently simply known as B and C. Now the green ring you see, this is the habitable zone, and it just so happens that the planet B seems to actually be in the habitable zone of this star system. And in the past we've actually even talked about this system because last year scientists discovered water molecules coming from this planet's atmosphere. It's also been analyzed many different times, and we now have a relatively accurate representation of its mass and radius and can start calculating what it can potentially have inside. Now unfortunately this star, like many other stars in our galaxy, is a red dwarf, but this one is not particularly that active. It's about half the mass of our Sun, And even though the closest planet, which is known as C, is technically very likely an extremely hot world similar to Venus, its neighbor is a lot more interesting and a lot more mysterious. Now, first of all, this is not truly an Earth-like planet because simply of the size and the mass. It's a lot more massive and a lot bigger in size than our Earth. If I were to compare Earth to this planet, this is sort of what it would look like. So in that sense, it's not truly an Earth-like object at all. This is technically either a super-Earth, basically an object that's a lot more massive and a lot larger than Earth, or possibly even what's known as a mini-Neptune, basically a small gas giant. Now, currently we don't really know what exactly is happening on this planet, but this is exactly what this study tries to figure out. Essentially, what they did is take all of the data we have about the planet and then use a lot of very powerful simulations to essentially create all the possibilities that this planet has, from being very similar to what you see here, which is technically a water world. This is basically a planet almost entirely made of water, but the scientists actually believe this is probably not really the case because of the way that planets form, to being more of a silicate world, so essentially similar to Earth, but with a very thick hydrogen atmosphere, or essentially a world that does have an actual surface, but on top of the world there is quite a lot of hydrogen, thus making it a very unique world. So even though technically it's still a terrestrial world, it does have a very, very thick atmosphere. In some sense, this would be kind of similar to what you would call a super Venus. And then they also looked at everything else in between, so maybe it's a mixture of a water world with a bit of a hydrogen and also a little bit of everything in it. Essentially, the main purpose of this study was to see how likely would we find something that could potentially host life or have at least some sort of a habitable liquid ocean. The reason for this is because in this region of the star system and with a relatively thick atmosphere, this planet has quite a unique chance to not only possess a very large ocean with some of the most habitable conditions we've seen so far, but at the same time it could also be this unusual, strange planet we've never really seen before, with extremely unique composition and somewhat interesting atmosphere as well. In other words, this could be the prime candidate for the atmospheric studies of James Webb Telescope when it becomes operational in a few years. Although don't get too excited about this planet just yet, because in terms of the actual location and distance, it is pretty far away, about 124 light years away from us in this location right here that you see on the map. It's also approximately 2.6 times larger than planet Earth in terms of size, and almost 9 times more massive than our planet. So this could mean that this planet has quite a lot of gravity on the surface as well. A single year on this planet lasts for approximately 33 days, and it's very likely also tidally locked to its parent star. In other words, it's probably always facing with the same side toward the star, although this is not really something we can confirm just yet. And that's because in certain situations, planets can actually acquire spin that's not really tidally locked. For example, collisions or even thick atmosphere can potentially change the rotation of the planet. We have a good example of this here in the solar system, Venus. But all of the previous studies unfortunately suggested that it's very likely this planet is more of a gas giant, simply because this is how planets usually form. So there would very likely be an extremely thick hydrogen layer, or basically something similar to what Saturn and Jupiter have. And then of course the inner core could potentially be a little bit different and possess certain materials, creating a kind of a terrestrial world underneath all of this hydrogen. But this is why the scientists decided to simulate all of this by giving the planet different parameters just to see how likely is it going to have liquid water and also be potentially habitable to, I guess, extreme life or actually any water life. And one of the main reasons is because if it does have a lot of hydrogen on the surface, it's very likely that the pressure inside is really high, so the water could actually not be even liquid anymore. It could be in either gas state or some sort of a supercritical state. Now this is what this planet looks like currently in all of the current NASA simulations, but this is a much older model and it hasn't really been updated just yet. And so, having simulated all of this using different conditions, including a lot of hydrogen or just enough hydrogen to fit the criteria, they discovered that there are a lot of different possibilities for liquid water to actually exist here. Obviously, there are conditions where there's no liquid water, it's either too hot or there's just not enough water to form any ocean, but there were also a lot of conditions where water did exist and created a world that potentially could have been habitable. Now, this is why this is probably, so far, one of the most likely sources for us to discover an actual ocean with potential existence of life there. And currently, the chance of finding liquid water here has increased dramatically. And because this planet is in the habitable zone of its star, it now also has a much higher chance of actually having life than even nearby moons such as Europa, Ganymede, or Titan. And at the same time, by using some of the more recent observations, they also found out that apparently there's a lot less methane and ammonia in the atmosphere of this planet, suggesting that it doesn't seem to fit the profile we initially thought it had. And because these two elements were below the level they expected, there's gotta be something going on in the atmosphere of this planet. Now, they don't suggest that it's aliens or that it's some sort of a bacterial life in the atmosphere, for example, but at this point we don't actually know. There are a lot of different methane anomalies in our own solar system as well, both with Venus and Titan, but it looks like this study just added another one of these anomalies for us to investigate in the future. Also, one of their main discoveries here was that you don't even need that much hydrogen for this planet to be the way that we think it is. The maximum amount of hydrogen it might have is about 6% by mass, and that's the extreme amount. If you compare this to planets like Jupiter and Saturn, where most of the things are hydrogen, that's a huge difference. The scientists here even suggested that it's very likely the actual level of hydrogen is much lower, making this really a very unique water world or terrestrial planet. And they even suggested that there's a chance that there could be just as much hydrogen as there is here on Earth. In other words, this planet even has a chance of being a very, very large, very massive Earth-like terrestrial planet with quite a lot of water in its atmosphere. So just to summarize, this right now is probably one of the most exciting exoplanets we've discovered, and even though it's kind of far away, and even though it's completely different from planet Earth in terms of mass and size, it still is the best chance we have so far of discovering some sort of an organism somewhere out there that is technically alien. But for now, that's really all we know, and until James Webb Telescope can actually pierce through these hazy clouds and try to discover what's going on here, we are unfortunately not going to know what's really happening on this planet. Hello wonderful person, this is Anton, and in this video we're going to be trying to answer the question of, well, how big is our Milky Way, our galaxy? Where is the edge of our galaxy? One of the recent studies tries to actually very thoroughly analyze this question and even gives us a rough estimate of where we believe the edge of our galaxy is. Well, it should come to as no surprise to you that we don't really know what our galaxy really looks like, mostly because we're looking at it from the inside. We've seen a lot of spiral galaxies that we think are possibly similar to the Milky Way, like this one right here, and we've even tried to simulate what this might look like by looking at it from the inside and then trying to basically extrapolate the outside. But so far we're not really sure on the shape, the number of arms, and obviously the actual full size of our galaxy. One of the recent studies from only a year or so ago actually established that our galaxy is very likely at least 120,000 light years in radius, which is practically the double the distance of the original estimate. In other words, even though we thought it looked kind of like this, in reality, it's practically double the size. We've also reanalyzed the mass, and today most scientists believe that Milky Way is probably the largest and the most massive galaxy in the so-called local group. We've always believed that the Andromeda galaxy that you see right here was larger and more massive, but most of the recent observations seem to tell us otherwise, so it does seem like Milky Way is larger and also more massive. But all of these observations are not really accurate, mostly because as of today we haven't really established where to stop measuring the actual edge of the galaxy. In other words, how do we actually establish where the galaxy ends and where the other one begins? And so this is what the recent study that you can find in the description below decided to do by both doing a lot of simulations using 3 different simulation systems and also trying to establish a kind of an official edge of where the galaxy should technically end. And it's very, very surprising because it's a lot farther than we initially thought. And one of the main reasons is because this, the sort of prototypical galaxy that we're all used to, is actually only a very, very small piece of what a true galaxy is. Today we know that apart from the actual galactic center and the disk itself, there are a lot of other structures inside the galaxy that are technically also part of it. There's obviously things like globular clusters that are connected to the galaxy. There's also a lot of gas around the galaxy itself, but most importantly, the vast majority of the mass is actually in the so-called halo. Now today, most scientists believe that this is consistent of dark matter, but there hasn't really been official proof of the existence of dark matter just yet. At the same time, apart from dark matter, halo also consists of a lot of individual stars, a lot of globular clusters, and a huge amount of dust. As a matter of fact, if I were to try to simulate what all of this looks like without trying to crash my computer, if this is a typical galaxy here, here's what all of this might look like if we were to kind of zoom out of here. This huge spherical object you see around the galaxy is essentially gas, stars, globular clusters, and dark matter. And the amount of gas and stars here is very likely at least similar to the total mass of the actual prototypical galaxy that you see right here. In other words, if you were to take all of this and turn it into a bunch of individual stars and gas, you also get a very similar amount of mass in the halo as well. And this is of course not including the mysterious dark matter. But one thing that this study confirmed is that it's very likely that none of this looks like a sphere. So this halo of gas, stars, globular clusters, and of course mysterious dark matter is very likely very differently shaped for every individual galaxy, depending on various galactic interactions that happen in that particular local group. So for example, for the Milky Way galaxy that's right here and the Andromeda galaxy that's right here, because there's a lot of gravitational interaction between the two, and also because the actual dwarf galaxies that you see right here also interact with the halo, they do sort of turn this into a somewhat different shape, and it's very difficult for us to predict right now what the halo of Milky Way currently looks like. I guess for now this is the best I can do because we just don't really know what the real shape is. Now at the same time, because the distance here is roughly around 1 million light years, it's practically equivalent to half the distance of Milky Way to the Andromeda, and assuming that the Andromeda galaxy also has a similar halo, they're probably already touching and interacting. And this also confirms another study that very recently discovered actual newborn stars being formed pretty much in the middle between the Milky Way and the Andromeda galaxy, which very likely resulted from the collision between two halos. So in other words, what all of this suggests is that not only is our galaxy much bigger and its edge much farther than we initially thought, but at the same time this also tells us that both galaxies are already colliding and creating a lot of new stars and a lot of new globular clusters. So even though we thought that this is maybe what the galactic collision would look like, it's already started. It's already going on, and a lot of new things will be generated in the next few billion years before these two galaxies finally finish combining and turning into a single galaxy, most likely called Milkdromeda. But I think what always surprised me is how much gas there is in this halo. Like I said previously, the total mass of gas here is essentially similar to the whole mass of the galaxy that we typically see. And although it's kind of difficult to understand or explain at first, but in reality it really makes a lot of sense, mostly because of how galaxies are born, how they grow, and how they interact with other galaxies and gas around them. So today we actually know that once in a while a typical galaxy will become what's known as an AGN or active galactic nuclei galaxy, or essentially what we sometimes refer to as quasars if you look at them from far away. These AGNs are normally defined by an extremely active supermassive black hole in the center that absorbs a huge amount of mass from all of the gas that flows into it, while at the same time creating these very powerful astrophysical jets. And these astrophysical jets, this is the picture from the M87 black hole astrophysical jet, kind of act like typical fountains. They throw out all of this matter really far away from the galaxy and sort of recirculate it back into the halo. But then once in a while, all of this halo gas accumulates into a big chunk and falls back into the center of the galaxy. So it's sort of like a self-feeding fountain of gas and energy. So once in a while the gas gets expelled, then it comes back and starts feeding the black hole again. And we've even observed this as what's known as Fermi bubbles right here in our own galaxy from the last such eruption. This was approximately a few million years ago, and this gas is slowly moving out into the halo, and at some point some other gas cloud might come back and restart the AGN inside the Milky Way galaxy as well. But because these eruptions are always very different, this is why the halo itself is not spherical. It always has these blobs everywhere, and including of course the interaction with other galaxies, it grows into different directions and creates this interesting, unusual shape that's always different for every single galaxy. But for our galaxy, using these simulations, the scientists established that the edge is probably around 1 million light years away, or roughly around 300 kiloparsec or so. But this value might also change as we discover a new dwarf galaxy in the vicinity, and as we understand how all of this sort of influences the size of our own galaxy. And one of the main reasons it's important to kind of understand what the total size of the galaxy is is in regards to calculating various galactic interactions. Here, normally, we don't really count the mass and the size of the galaxy when we try to, for example, calculate a velocity of an escaping star or an interaction with another dwarf galaxy. But by knowing exactly how large and how massive the whole galaxy is, we'll be able to get much more accurate results in the future. And most importantly, this will help us one day understand and explain how the Milky Way galaxy was formed and how, essentially, we came to be as well. Because all of this is sort of connected. And just to give you another visual representation of this, here in Space Engine, you can actually even see some of these halo stars and halo globular clusters. They're basically these random stars here and there, like there's one right there, that appear away from the galaxy, but within the bounds of the so-called galactic halo. And they do extend quite a lot, up to several 100,000 light years. And what's interesting is that some of these stars are actually really new. They're baby stars. So the only way that they could have been created is if there was a lot of gas circulating around the halo, and once in a while it would actually initiate the star formation. And as you can see in this particular case, this star even has its own planets. So maybe one day we'll discover a very unusual planet somewhere outside of the galaxy, looking at us and being able to actually see what the shape of the galaxy is. So it's very possible that one day we'll discover such a star with planets orbiting around it, but being completely outside of the actual plane of the galaxy. Hello wonderful person, this is Anton, and welcome to the hottest planet in the galaxy, and maybe even the universe. Today we're going to be talking about the planet known as Kelt 9b and a new discovery coming from this very unusual object that technically should not even be called a planet anymore. So if you were to find yourself on the surface of Kelt 9b, you would discover a lot of really interesting features, including some of the most unusual clouds ever. Clouds made up of different silicates, rocks, and metals, and that's something that you don't really see anywhere in the solar system. This unusual planet is so hot for one reason. It's basically really close to its parent star, and its parent star is one of the hottest stars possible. The star known as Kelt 9 is what's known as a B-type star, and it's over 10,000 degrees in temperature. That's about double the temperature of our own sun. And the surface of this planet is a ridiculous 4,300 degrees Celsius, or roughly around 7,700 degrees Fahrenheit. So this right here, as of today, is the hottest planet we've discovered. But the recent study that you can find in the description below suggests that something else is happening on the surface of this planet that in a sense doesn't even qualify it as a planet anymore. The temperature here is so ridiculously hot that they literally can't be molecules anymore and become atoms. And they stay this way until they somehow make it to the other side of the planet, where it's just a little bit cooler so they can get reassembled into molecules once again. So what this actually creates is a very strange object. On the bright side, you have all of these atoms of various molecules that used to be here, but on the dark side, you get actual molecules once again. So things that we typically think of when we think of a planet, like for example silicate oxides which make up rock in our planet, or even things like CO2 and oxygen which we breathe and make up our atmosphere, do not exist on the brighter side of Kelt 9b, which in a sense makes half of this planet not really a planet at all, but instead some sort of a strange plasma-like cloud. But let's talk a little bit more about this planet before I continue about the study. So Kelt 9b is one of these so-called hot Jupiters, of which we discovered quite a lot of various planets. And one of the main reasons we've discovered so many already is really because they're really massive, they're really close to the stars, and so they're exceptionally easy to see. And a typical hot Jupiter would look something like this. This is a very large, very massive planet extremely close to the star. And not only can you see these Jupiters pass in front of the star very easily, but you can also see them pull on the actual star, thus making it move across the night skies, which you can kind of see from this velocity graph right here. So these planets are exceptionally easy to find, and we've discovered quite a lot of them already. But some of these hot Jupiters are even more unique. A lot of them are so-called puffy planets, a lot of them are very low in density and are known as cotton candy planets, but some of them, like Kelt 9b right here, seem to be even weirder, because as I mentioned, they don't seem to be planets anymore. They seem to qualify as something entirely different. Half planet, half some sort of a plasma cloud. Now, these conditions are obviously created by the very powerful Type B star that this planet orbits, and because the distance to the star is roughly around 3% of the distance of Earth to the Sun. So the amount of radiation this planet receives is absolutely ridiculous. And today we think that the UV radiation from the star is actually also slowly evaporating the planet, so you can kind of see the emissions coming out of this planet as it slowly orbits the star. A single orbit here is about 1.5 days, but the thing is, because this planet is about 2.8 times the mass of Jupiter, it will probably take it a very long time to finally evaporate or change into something completely different. We don't really know how these planets evolve, we don't even understand what exactly is happening here, but we understand that the molecular dissociation into atoms seems to be a common sort of thing amongst these planets. This is not the only planet that we think has this kind of an unusual feature. And also, interestingly, some of these atoms are not even things that are pretty common here on Earth. A lot of them are, well, for example, iron and titanium. So this object actually seems to have very unusual formation of, I guess, what you would call metallic clouds, that are these plasma clouds forming in front of it, or basically between the star and the planet, and then reforming into molecules on the other side. And since the most common element in these planets is usually hydrogen, it seems that even hydrogen is doing this as well. In other words, this planet changes hydrogen, which is usually H2, into these unusual dissociated atoms of hydrogen that then turn back into normal hydrogen clouds, or the very hot hydrogen clouds, on the dark side. And at the same time, scientists behind the study discovered that the difference between the bright side and the dark side of this planet doesn't seem to be too big. And this of course suggests that there's gotta be some kind of a heat flow going on this planet, and so the heat circulates around it even though the planet is always tidally locked. At the same time, the central heat spot of this planet is not actually in the center. So in other words, it's not somewhere here, but is instead shifted a little bit. And this is somewhat difficult to explain right now, but it might involve some sort of a collision that happened in the past that shifted this planet and changed its composition. But if not collision, it could also be explained by really strong winds on the surface that change the actual hotspot by transferring the heat away from the center. So in some sense, this could also be explained if the planet is spinning really fast. And because of the proximity to the main star and because of the other features of this object, it also seems to have a direct effect on its star. In other words, as you can see from this image created by Evgeny Shkolnik, the planet itself seems to interact with the magnetic field of the star and thus cause flares and all kinds of other effects on the star itself. So in other words, these planets now become kind of integrated with the star's behavior, which thus reinforces the idea that these are no longer planets but instead these strange objects that create all of these features that do not exist in other star systems. We even have a very specific way to call these types of stars and these types of interactions. They're known as star-planet interactions, or SPI for shorts, and there's an entire body of studies dedicated just to this topic alone. And from all of the other unusual hot Jupiters we've discovered, we also realized that many of them have very strange orbital parameters. In many cases, they either move very differently from other planets, or have somewhat inclined orbits, or in many cases they also seem to have opposite orbits, retrograde orbits, which are somewhat difficult to explain. Now this could be one of the reasons why these planets were able to get so close to the star to begin with. If they're orbiting against the flow, maybe there are more collisions happening to these planets, so they slowly make their way toward the star and thus become engulfed by it eventually. But at the same time, it's very likely that something else entirely happens in these star systems to give these stars such a strange orbit. And because of their unusual orbit and their position in the star system, it's also very likely that many of these planets become what's known as disrupted planets. In other words, they become either destroyed or fall apart, creating smaller pieces, thus turning a larger gas giant into a bunch of smaller objects. Now this is obviously not something we can prove very easily, but we've already seen at least one other system known as WASP-47 that seems to have several Earth-like and Neptune-like objects orbiting really close to the star, and there is an indication that maybe these were actually the result of a disrupted planet. In other words, they were created by a much larger hot Jupiter-like planet that slowly fell apart, creating these smaller pieces. So basically, there is still a lot of different mysteries to solve in regards to these hot Jupiters, and more specifically to the hottest planets out there, such as Kelet 9b. And the reason I wanted to create this collision right here is because I wanted to create a much more realistic image of what Kelet 9b might really look like, because this explosion now generates this very powerful and very large plasma cloud on the surface. Now this is a much better representation of what Kelet 9b might be like. This temperature here is probably around 5000 degrees, and it seems that a lot of material here on the surface would very likely turn into plasma and into atoms, and then change into something different on the opposite side. So this here is a slightly more realistic image of what's happening here. There's no real name for these objects just yet, we don't really know what to call them, but technically they're half cloud, half planet, and they also seem to have a direct effect on the parent star. We don't really know if these objects existed in the solar system, but there's a very high chance that they did. And what happened to them is another mystery. Because, for example, what if our planet Earth was actually a result of a disrupted hot Jupiter that used to exist in the solar system? This would open up an entire new study that would hopefully one day help us understand how planet Earth formed and how other planets evolved as well. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery coming from the region where Betelgeuse is located. Well, technically a little bit farther away from there, the so-called Orion Molecular Cloud Complex. This is where a lot of new stars are being made right now, and we've discovered something really interesting there. So by now you probably already know that Betelgeuse did not go supernova, it did not explode, and this is kind of something we've expected. It's now actually even brightening, so in that sense, for now at least, it's no longer interesting to us. But there are other things in this region that are really interesting. Specifically, not so far away from Betelgeuse, or technically where Betelgeuse was originally formed, is the so-called molecular cloud known as the Orion Molecular Cloud. This is sort of what it looks like in real life. This is an actual picture taken by the Hubble telescope, and this is where a lot of new stars are being formed pretty much on regular basis every single year from all of the dusty material present here, and then begin their lives as actual star systems. And because we're so interested in finding out how all of these stars generate, and most importantly, in understanding how planets then form from these new stars, this is where a lot of scientists try to investigate many different secrets of the universe. And so in one of their recent studies, that as always you can find in the description below, the scientists were looking at this molecular cloud and they discovered something really interesting. They discovered what I guess you would call a baby star, or not even a baby technically, an embryo star. An object that will become a star relatively soon but is not a star just yet, and this is technically our first discovery of such objects. Now today we have a pretty good grasp on understanding how planets form and how stars form, but it's still not really perfect. For example, we know that all of the star systems and all of the planetary systems start from this somewhat familiar to us planetary disk. We've seen this in a lot of different star systems, and pretty much all of them more or less look the same, or at least very similar. They all have the same properties, they all seem to progress through the same similar steps, and thus we believe this is exactly how our own solar system was born as well. It started as a kind of a cloud, then coalesced into a disk-like formation, and then eventually when the star in the middle became active and became an actual nuclear reactor, it sort of expelled a lot of the dust, and whatever was left over became planets. And some of the larger planets like Jupiter and Saturn may have even been created before the star became active. But we don't really have a very good understanding of what happens right before that, specifically the process of molecular cloud to disk formation. And one of the main reasons is because a lot of the younger stars are basically just clouds of dust, and it's really difficult to see through them. Whatever is happening in the middle is almost impossible for us to see with a regular telescope and even with a more advanced radio telescope. And so only some of the more advanced telescopes like the so-called ALMA telescope, which is one of the most advanced radio telescopes we have, are able to actually even discern what's happening in these clouds. Because there are 66 telescopes connected as a kind of a radio station, they're able to pierce through a lot of dust and see what's hiding behind all of the dust generated by the formation of baby stars. Now, what did the scientists discover? Well, the good news here is that they discovered several different stars in different periods of their formation, and they were able to thus compare them to our actual theoretical knowledge. For example, one of the stars has already undergone a collapse and is now becoming a kind of an opaque central region with something in the middle. Once again, not a star yet, but an object that's about 170 degrees Kelvin in temperature, which is, I guess, about minus 100 degrees Celsius, pretty cold, but much warmer than just regular vacuum. So something is already going on in the middle there. They also discovered an object that does not have any emissions yet, but the temperature on the inside is already much higher. And by the way, the names of these objects are right here above them. They then discovered another object where the outflow has already begun because of the way that the star starts spinning. And we expect all of the new stars to have these protrusions or these outflows, as a lot of matter gets expelled from two directions as essentially things start spinning. We obviously see these pretty much everywhere in the universe, including black holes, neutron stars, white dwarfs, and so on, but even early stars have them as well. And the last object even started to have some sort of a disk in the middle and a much stronger outflow, but also a lot more dust that's blocking the view as well. In other words, they discovered 4 different eras of a formation of a typical star, which will eventually result in this, which is of course what all of these protoplanetary disks that we have here that we've seen everywhere in the galaxy pretty much look like on the inside. And at least one of these objects even had a potential partner that's being formed with it that will either become a binary system or maybe have some sort of a very large super Jupiter-like object orbiting with it, or possibly even a brown dwarf. But since this is just the beginning of these stars being formed, it will still take millions of years for them to become anything similar to what our Sun looks like, much longer to become an actual mature star, and possibly even up to 1 billion years to become a stable star system with planets in stable orbits. This study also reveals the average size and the mass of these objects, and on average they have a mass of about similar to what our Sun has. Obviously they will probably decrease in mass as they grow because a lot of the material will be expelled, but this also means that they might become either red dwarfs or somewhat small G-type or K-type stars. And in terms of the actual size, you'll see here that the average size is about 1,000 to maybe 1,200 astronomical units. This here being equivalent to about 30 times the distance to Pluto. So these are really large objects, but they will obviously become more compact as they grow. And one of the interesting discoveries here is that even though on average all of these younger stars appear to be the same in size as older stars, they seem to be also a lot more massive, which suggests that they do lose a lot of mass as they grow, probably through various violent emissions that occur right here. Now this is probably how most of the younger stars lose their mass, but there could be other effects as well, we just don't really know what they are yet. And although the typical older star will look somewhat perfect in terms of the actual shape, it will be almost a perfect ring, all of these younger stars were a lot more blobby and a lot less predictable in terms of the shape. So even though most of them end up somewhat perfectly ring-shaped, they do start as completely irregular and unpredictable shapes, before becoming something like this. But even though right now we don't really have many more answers about this observation, there's going to be a lot of follow-up studies that will probably answer a lot more questions. One thing discovered so far is that we now understand that this whole process of, I guess, the cloud-like formation into the early protoplanetary disk takes a few thousand years. We always were kind of curious, how long does it actually take for a star to go through all of these stages? Some scientists suggested that it's a very fast process, possibly a few hundred years, but some scientists thought it was maybe a few thousand years. And it looks like, just judging by what we've seen so far, it does take at least 6,000 or so years to go from this to possibly this and eventually become a protoplanetary disk that then leads to an active star that then acquires planets as well. And one of the reasons they think it takes so much longer is because of various magnetic interactions as the actual disk starts spinning around and producing a lot of rotational and magnetic effects. So as the star starts collapsing, it actually, because of the spin, starts living a little bit longer and takes a little bit longer to actually acquire this beautiful disk-like shape. And so even though a lot of people were disappointed that Betelgeuse did not produce the light show we expected it to, the other discoveries coming from the Orion system are also pretty exciting. Unfortunately, all of the news about Betelgeuse kind of covered other excitement about the Orion clouds, which is why I decided to talk about this paper as well, because this discovery is pretty interesting. Hello wonderful person, this is Anton, and in this video we're going to be talking about the first ever discovery of the moment when the star transitions from being, well, a star to what's known as a remnant. So in some sense, we may have just witnessed the death of the star, although technically it's also the birth of the remnant. So let's start this with a bit of a history. Back in 1700s, specifically over 300 years ago, the famous William Herschel, one of the first and most prolific British astronomers, while using his homemade telescope, witnessed some unusual objects he couldn't really explain. They did look kinda like Jupiter and Saturn, and also seemed to possess a kind of a cloudy appearance, and because of this he decided to refer to them as planetary nebula. Basically kinda like planets and clouds mixed together. Back then he obviously had no idea what he was looking at and even how far away it was, but with time scientists obviously realized that what they were looking at was actually not planets at all. This was the remnants of stars, and these are some of the most incredible and some of the most beautiful objects in the universe. There are all kinds of different planetary nebula out there, and their formation usually is responsible for not just the shape that they form, but also for all of the other colors that do form as a result of the emissions of the central object. The object in the middle is basically a white dwarf, a star very similar to our Sun. Which is of course why it's very likely our Sun is actually going to become something similar to this as well, in approximately 6 to maybe 7 billion years from now. We've discussed the so-called stellar evolution in some of the previous videos, but just in a nutshell, basically our Sun is somewhere right here, and it will eventually kind of turn bigger and bigger, cooler and cooler, and expand to the point where it's probably going to swallow Mercury, Venus, and possibly even Earth. And then it will actually start expanding and kind of releasing some of this gas here, which will result in a very large formation of a dust cloud around the solar system. To give you an example from something a little bit more recent, Betelgeuse, for example, is also doing this right now. It's sort of throwing out a lot of gas, and today we're pretty certain that the reason Betelgeuse changed from this to this, dropping its actual brightness by about 70%, is actually because some of this dust kind of covered the part we're seeing from planet Earth. So essentially all of this gas will stay there in this region until Betelgeuse transforms into its remnant. And once the remnant becomes the only thing in the middle, it's going to be emitting a lot of different ultraviolet light, which will then be absorbed by all of this gas and produce these beautiful colors you see here. So essentially what these nebula are, these planetary nebula specifically, are the interaction of the UV light from the small object somewhere right there in the middle with all of this dust deposited over essentially a few thousand and possibly hundreds of thousands of years. And depending on the actual material that the UV light strikes, it will produce different types of colors. But we've never really seen these objects being formed, and more specifically, we've never been able to see inside of this part because it's really dusty and it's hard to see through it. And so for this study that you can also find in the description below, the scientists who investigated the star known as W43A, located at a whooping distance of about 8,500 light years away from us, had to use the very powerful ALMA telescope that can actually see through dust and thus analyze what's happening inside of the actual star system. And to their surprise, they discovered that this star has just transformed from being, well, a star, a main sequence star, to what's known as a remnant that is releasing all of these incredibly powerful jets that are moving across the star system and are going to eventually end up creating the beautiful nebula that we'll basically call a planetary nebula. And these events don't really last very long, so discovery of this object is very lucky for us. The typical planetary nebula normally lasts about 10 to maybe 100,000 years. But this initial stage, when the star starts throwing out all of this material, only lasts for approximately a few hundred years. So finding such an unusual object was extremely lucky for these scientists. Now, the actual image they took is this right here, and what you're looking at is essentially a 60 years old planetary nebula that has just started growing, with the middle here being the star remnant, and these two objects are being the actual jets that it created. The interesting thing about this object is that it's a binary system, and so the formation of these jets is very similar to what you see in here. The remnant itself is sort of absorbing a lot of the mass from its partner and is throwing it out, creating these unusual formations. Now, this is really important because most of the planetary nebulae we've seen so far usually fall into two categories. They're either like this one right here, they have really unusual projections on both sides, or they're more or less circular like this one here. The circular ones seem to be the ones that form from individual stars, whereas we're now pretty much certain that the longer ones are formed from binary systems. In other words, the simulation right here is about to show you how this happens. These jets, as they propel away from the star, will eventually form these really long beautiful formations that can then be seen across various planetary nebula in the night skies. And right now, this baby planetary nebula, if we were to kind of zoom in and try to visualize this using modern understanding, it would look probably something like this. So what you're seeing here are the binary stars right there in the middle, the jets being propelled from two sides, and all of this dust and all of this gas is slowly being illuminated by the powerful projections from the star itself. It's not really creating the planetary nebula just yet because it still has some gas that's sort of mixing with the star and is hiding the UV light, but eventually once the actual shell is gone and the UV light starts illuminating everything, the planetary nebula is probably going to resemble something like this. And by the way, this thing in the middle, we do have a name for it. It's usually known as PNN or Planetary Nebula Nucleus. And today we're absolutely certain that these objects are responsible for sort of propagating and mixing a lot of various materials across the galaxy, allowing for other stars to eventually absorb this material and create their own systems. And so what we're looking at here is the end of one star system, but also the future of a lot of other star systems that will probably gather this material and create their own planets and possibly even smaller stars. And interestingly, there's at least one unusual discovery here which sort of changes our perspective on these actual jets as well. We've always believed that these jets were not really moving that fast, maybe 10 to 20 kilometers per second. But it turns out, when they measured the speed here, they realized it was moving closer to about 170 kilometers per second. And this is the distance that it traveled in approximately 60 years. This of course means that there are still a lot of things we don't really know about planetary nebula, and a lot of things we don't really understand about evolution of stars in general. But studies like this help us understand a little bit more, and obviously learn about how all of these beautiful formations across the galaxy formed and what they mean to the future of our own galaxy. And as I mentioned previously, this is actually a really rare object. There are probably around 400 billion stars in the galaxy, but we've only discovered about 15 of these objects, even though normally they're not really that difficult to see. This of course suggests that these particular objects really don't exist that long. We're looking at something that's not going to last very long and unfortunately is going to disappear within approximately 100 or so years from now. But for the next 100 years, scientists will have a chance to study this in a little bit more detail. But anyway, that's kind of all I wanted to mention in this video. It's really one of the more unusual discoveries of the last few months, but it's also something that will help us understand the evolution of our own sun as well. As I mentioned, the sun will also become something very similar to what you see right here, but we're not really sure what's going to happen to planet Earth, and we're not really sure what's going to happen to other planets as well. And even though we might not be around anymore, by that time it's very likely human species might not even exist, or at least move somewhere else, it's still kind of important to understand what's going to happen to the solar system in a few billion years.